In this example, we have this steel platform with an irregular shape and the columns distribution as we can see in the 3D view. So for this model, we're not allowed to add columns anywhere. We only can add columns at these corners as we can see, in addition to 4 inner columns. So in total, we have 9 columns. We can see that these columns are braced together in both directions to provide rigidity and stability for the structure in both directions. And then we have the main girders spanning in one direction, in the Y direction. So part of these main beams are supported on another transfer beam. As we can see, we will go and show the extruded view. So in this direction, we have these beams supported on these transfer beams at these columns grids, and on the sides they are supported on these long span girders as well. And these beams, which are supporting the main beams here, in their turn are supported above these huge girders, 28-meter girders. So the load path is not direct. It's not always joists to girders to column. No, we have lots of transfer beams due to architectural constraints. Now we're assigning the live and the superimposed dead load, 5 kilonewton per meter square for live load and 4 kilonewton per meter squared for dead load. We have RC on metal deck, 150 millimeter filled deck with the ribs distribution and the topping as shown. And as we said, the load will be transferred from the deck to these secondary beams or the joists, and then it will be transferred to these beams in the Y direction, and then these beams will transfer the load to the transfer beams, and at the end the load will be carried by the columns and it will be transferred to the foundation. So the load path is not direct, and this structure we can call it an irregular structure due to some architectural constraints. Now we will run the model. In this example, we will focus on the gravity loads only. Now after we run the model, now we will design. We can see that all beams are passing, and we will also check the composite beams for simply supported beams. We can see also that all beams are passing the unity checks. For sure, we can go and show other design info, the deflection ratios, and other info as well. Now, after we do the design, we will not go into details for designing such structures and the design parameters. We will now focus on checking the serviceability or the deflection of the floor, and to show the common mistakes some engineer might fall for. We need to do some steps before checking the deflection for this model. First of all, we need to account for the weight of the connections. We have lots of beams, joists, and bracing. So the connections weight need to be considered. This is also for design, not only for deflection. But now we will show how to consider the weight of the connections in the model where we have composite slab or concrete slab modeled in the same model. Typically, some engineers go to the load pattern and go to the dead load and use the self-weight multiplier. So here, instead of having one multiplier, we have 1.1 or 1.2. So this 15 to 20% will account for the weight of the connection. However, when we have a concrete slab modeled, this is not accurate and over conservative because the weight of the concrete slab will be considered in the dead load pattern. So adding 20% will adding a 20% not only for the steel members weight, but also for the concrete slab weight, which is a huge number. So how to solve this issue? We can do it in a very accurate way. We unlock our model and we will go to the material property. So in this model, we are using the high grade S355. We show the material and here we will adjust the weight of the steel material only without changing the weight of the concrete. So here simply we will go and multiply this number by 15%. So here the weight is adjusted to account for the connections, and that's all we need to do. Second, if we are using direct analysis method, in this method, one of the conditions is to decrease the stiffness of the members. And this can be seen when we run our model again. Let us design, and we will see for this member, for example, we have reduction on the axial and the flexural stiffness of the member. This is during analysis. So what to do now? We go to the View Revise Preferences and we select Effective Length. We don't need to modify the other parameters. And then we save this model. If we want to have a separate model for deflection and have the main model ready for strength check, we can save it and call it for deflection check. In this example, I will only consider working on the same model. Now I will design again. I will unlock the model and I will run one more time. So remember, this model will be used only for deflection. I run again, and here I can see that there's no reduction for the axial or the flexural stiffness during analysis. Now we have a combination for dead load plus live load. We will check the model for deflection 2 combination. As we said, for the composite beams, the software automatically check the deflection for the composite beams, the live load, and the total load. So it checks the deflection for construction dead load, the post concrete deflection, the live, and the total. Here for sure, if I want to consider adding shear studs, I can choose the percentage of composite action and I will get the final deflection value. However, for the main beams, we simply go and check the deflection through the moment 33. And we will go and check the deflection for each member to ensure that this member is not deflected more than the allowable limit. We will start with these beams. Right click, and these beams length is 16 meter and the actual deflection under dead plus live load is 55 millimeter. So the allowable as per ASCE and IBC is the length divided by 240 for dead load plus live load. So 16 meter over 240, we have around 66.7 millimeter. This is the limit. So my member's deflection is less than the allowable, so it's okay. We need to also check the deflection under live load, and it's the length of the beam divided by 360. So the limit is 44.4 millimeter and the actual deflection under live load is 21 millimeter. So it's okay as well. We do the same for all other beams. We start with the simply supported beam or the beam with the highest positive moment because this will deflect the most. Here, this beam is 18.67 meter and the deflection is 38 millimeter, so it's also below the limit. This beam's deflection is similar to the beam at this grid. It's also below the limit. We do the same for all other beams. For example, this beam is 28.84 meter and the deflection under dead plus live load is around 76 millimeter. However, the allowable deflection for this beam is 120 millimeters. So we divide the length over 240, and for sure we need to check deflection under live load. We divide the length over 360. So as we can see, all members are passing strength and deflection requirements, but this is not the case. Here's the mistake many engineers might fall for, is not checking the accumulative deflection, especially for this type of structure. So here, if I go and I check the deformed shape for the dead load plus live load, I will use the contours just to show us the most deflected areas. We will see that this area is deflecting more than all other areas. Let us check the deflection here. It's around 124 millimeter. Here it's around 127 millimeter. So the deflection at this area is reaching 127 millimeter, which is excessive. This deflection value is a result of an accumulative deflection of several beams. If I go back and check the deflection, we will see that the deflection for this main girder relative to beam ends is almost similar to relative to beam minimum and also to the absolute, because it's the main beam that is carrying all other beams and it's supported at its ends to the columns. For sure, the absolute value will be slightly higher because it accounts for the rotation of the beam to column joint. To clarify that more, for example, we have this column and we have this beam which is supported at the column on the right and at the frame to the left. So this deflection, we read here, when I have both ends of the beams are fixed in translation. So here the deflection value is 0 and here the deflection value is 0. So this deflection relative to the beam ends is, for example, 15 mm. In other words, this beam will deflect at the midspan 50 mm more than it deflects at ends. So here I set the deflection at ends to 0 and I measure the deflection for the beam at the midspan in relation to the ends. However, in real life, this will not be 0 because I'm focusing on the relative deflection of the beam. I get this value, and this is the first number we read here when we say relative to beam ends. We have another deflection. We read it from the diagram, which is relative to beam minimum. So in this case, this joint is deflecting. Assume it's deflecting 35 mm. So the deflection shape for the beam, let's call it beam A, will be like that. In addition to the deflection we measured before, which is the 50 mm. So this is the total deflection. And for sure, the total deflection will be more than the 50 mm. Here from the triangle, we can get this value, x, and the deflection relative to the beam minimum will be x plus 50 mm. and this is the value we get here. Why this number is significantly larger than this number? Because this point is deflecting significantly related to this point, which is rigid at the column. Here, it's near the midspan, so it's deflecting much more than the other end. So what about the third number, which is the absolute? The absolute is the highest deflection for the beam in relation to the undeflected shape, taking into account all cumulative deflection values. So number 3 will be somewhere here, because here also, due to the rotation of the joint, it will have a value of deflection in the Z. And if this beam in its turn is supported on another beam, so all the deflection values will be seen at the absolute. Let us show this beam, for example, the secondary beam here, which is connected between these two beams, which in their turn are connected or supported by these two girders, which are supported by one column at one end and this huge girder at the other end. So this beam, relative to its end, it's deflecting 28 millimeter. We will see now that the relative to the frame minimum deflection will be close to this value, because at both ends it's connected to the mid span, approximately the mid span of these beams, which are similar in length and stiffness. However, the difference that one of these beams is connected to the girder here closer to the midspan, and the other one is connected closer to its end. So we can see that this number is close to the relative to the beam ends. However, the absolute value will be much larger, because this beam will deflect for sure. Firstly, this beam will deflect. At the ends, these beams will deflect, and the supporting beam, this one, will deflect, and finally these 28-meter beams will deflect at the midspan. So all the deflection, the accumulative deflection, will be seen at the absolute value. Here we can see that the absolute value is reaching 150 mm at these beams, which we saw earlier is deflecting the most. So this is the structure after the modification. For sure, each structure is unique and the solution will differ from a case to another. In this example, what we did here is that we added this additional girder, and this girder is connected directly to the column at one end and to this rigid point at the other end, which is supported by these braces. So this girder now will be supporting these main beams, and it will significantly reduce the deflection, because now the load path is direct to the column and it will carry a good portion of this floor based on the tributary area for sure. So let us see first the moment you can see that this beam, although it's deflecting around 66 millimeters, however, it's still well below the limit. Also, these main beams now are deflecting much less than what we saw before. To see the total deflection value from the contours, we can see now that this area is not deflecting much, and actually other areas now are deflecting more than this area. However, all the deflection values are within limits. So now my structure is rigid and is well designed. Deflection is within limit, and I can confidently say that I have a safe structure by introducing this main girder. So this is the issue when we have a lot of transfer beams and the load path is not direct from joists to girders to column. Always we need to check the accumulative deflection and ensure that the total deflection at my floor is within the acceptable limits. For sure, this limit needs to be confirmed by the architect, the mechanical engineer to ensure that, for example, if we have a terrace, that the deflection will not result in water ponding and that the drainage will work well. Also, if I have a brittle material like a curtain wall or a glazed wall sitting at some flexible areas in my structure to ensure that the allowable deflection will not impact these elements.